In geometry, a hypercube is an n-dimensional analog of a square and a cube. It is a closed, compact, convex figure whose one skeleton consists of groups of opposite parallel line segments aligned in each of the space's dimensions, perpendicular to each other and of the same length. A unit hypercube's longest diagonal in n dimensions is equal to. An n-dimensional hypercube is also called an n-cube or an n-dimensional cube. The term measure polytope is also used, notably in the work of H. S. M. Coxeter, but it has now been superseded. The hypercube is the special case of a hyperrectangle. A unit hypercube is a hypercube whose side has length 1 unit. Often, the hypercube whose corners are the two endpoints in Rn with coordinates equal to 0 or 1 is called the unit hypercube. Construction. 0. A point is a hypercube of dimension 0. 1. If one moves this point 1 unit length, it will sweep out a line segment, which is a unit hypercube of dimension 1. 2. If one moves this line segment its length in a perpendicular direction from itself, it sweeps out a two-dimensional square. 3. If one moves the square 1 unit length in the direction perpendicular to the plane it lies on, it will generate a three-dimensional cube. 4. If one moves the cube 1 unit length into the fourth dimension, it generates a four-dimensional unit hypercube. This can be generalized to any number of dimensions. This process of sweeping out volumes can be formalized mathematically as a Minkowski sum. The d-dimensional hypercube is the Minkowski sum of d mutually perpendicular unit-length line segments, and is therefore an example of isonotope. The one skeleton of a hypercube is a hypercube graph. Coordinates. A unit hypercube of n dimensions is the convex hull of the points given by all sign permutations of the Cartesian coordinates. It has an edge length of 1 and an n-dimensional volume of 1. An n-dimensional hypercube is also often regarded as the convex hull of all sign permutations of the coordinates. This form is often chosen due to ease of writing out the coordinates. Its edge length is 2, and its n-dimensional volume is 2n. Elements. Every n-cube of n greater than 0 is composed of elements, or n-cubes of a lower dimension, on the dimensional surface on the parent hypercube. A side is any element of dimension of the parent hypercube. A hypercube of dimension n has two n-sides. The number of vertices of a hypercube is the number of m-dimensional hypercubes on the boundary of an n-cube is, where an n denotes the factorial of n. For example, the boundary of a 4-cube contains 8 cubes, 24 squares, 32 lines and 16 vertices. This identity can be proved by combinatorial arguments. Each of the vertices defines a vertex in a dimensional boundary. There are ways of choosing which lines that defines the subspace that the boundary is in, but each side is counted times. Since it has that many vertices, we need to divide with this number. This identity can also be used to generate the formula for the n-dimensional cube surface area. The surface area of the hypercube is. These numbers can also be generated by the linear recurrence relation, with and undefined elements equals 0. For example, extending a square via its 4 vertices adds 1 extra line per vertex, and also adds the final second square, to form a cube, giving equals 12 lines in total. Related families of polytopes. The hypercubes are one of the few families of regular polytopes that are represented in any number of dimensions. The hypercube family is one of 3 regular polytope families, labeled by Coxeter as gamma n. The other 2 are the hypercube dual family, the cross polytopes, labeled as beta n, and the simplices, labeled as alpha n. A 4th family, the infinite tessellations of hypercubes, he labeled as delta n. Another related family of semi-regular and uniform polytopes is the Demi Hypercubes, which are constructed from hypercubes with alternate vertices deleted and simplex facets added in the gaps, labeled as H gamma n. Relation to n simplices. The graph of the n hypercube's edges is isomorphic to the Hasse diagram of the simplex's face lattice. This can be seen by orienting the n hypercube so that two opposite vertices lie vertically, corresponding to the simplex itself and the null polytope, respectively. Each vertex connected to the top vertex then uniquely maps to one of the simplex's facets, and each vertex connected to those vertices maps to one of the simplex's n3 faces, and so forth. And the vertices connected to the bottom vertex map to the simplex's vertices. This relation may be used to generate the face lattice of an simplex efficiently. Since face lattice enumeration algorithms applicable to general polytopes are more computationally expensive,